a new movie drops, and suddenly content delivery network cache hit ratio plummets from 95% to 40% in the Northeast US. Users see buffering and downgraded quality. The root cause? A cache miss storm that cascades from edge to origin. Let's break down how Netflix handles this. Welcome to TheCodeForge. Before we dig into that production issue, let's cover Design Netflix. Netflix system design is the architecture of a global streaming platform that delivers video with sub-second startup latency. The core mechanic is a multi-tier caching hierarchy. Content delivery network edge caches hold popular content, regional caches handle misses, and the origin store serves the full catalog. Let's start with the numbers that drive every decision. 250 million subscribers each watching 2 hours per day means 500 million hours of streaming daily. Peak bandwidth reaches 250 Tbps, and a 500 ms increase in startup time drops retention by 20%. Here's a quick calculation of the scale. 250 million users times 2 hours gives 500 million watch hours per day. At peak, 50 million concurrent streams at 5 Mbps each require 250 Tbps bandwidth. Storage for all encoded versions is around 20 petabytes. Netflix's architecture breaks into 4 layers. Client apps, content delivery network layer with open connect appliances, backend services as microservices running on Amazon Web Services, and data layer using Cassandra, EV Cache, and simple storage service. This diagram shows the flow. Client apps connect via HTTPS to the content delivery network, which serves video chunks. The API gateway routes to backend microservices, each with its own data store. Netflix doesn't serve a single video file. Each title is encoded into 50+ versions, sliced into 2-second chunks. The client's ABR algorithm monitors download speed and buffer level to select the appropriate bitrate. Open Connect appliances are deployed inside ISP data centers for low latency. This is a simplified Open Connect cache. It stores chunks in a concurrent hash map. On a miss, it fetches from the origin and caches the result. In production, eviction policies and backpressure are critical. Netflix runs hundreds of microservices. The critical pattern is the circuit breaker, implemented via Hystrix. If a call fails or times out, the circuit opens and subsequent calls fail fast. Chaos Monkey randomly terminates instances to force resilience. This Hystrix command wraps a call to the playback service. It sets a 2-second timeout, a 5-second sleep window, and a 50% error threshold. If the call fails, it returns a fallback response. Netflix uses multiple databases: Cassandra for high-write user metadata, EV Cache for sub-millisecond session cache, and simple storage service for video storage. No single database can serve both write-heavy ingest and read-heavy serving. This table shows which database Netflix uses for each use case. Cassandra for user profiles, EV Cache for session data, simple storage service for video assets, and Elasticsearch for logs. Netflix's recommendations are responsible for 80% of content discovery. The system uses offline training on Spark to produce embeddings, then online serving with nearest neighbor search to return top titles in under 200 ms. This simplified function computes dot product between user and item embeddings, then returns the top 20 indices. In production, this uses approximate nearest neighbor search via FAISS. Video uploading is bottlenecked by transcoding, not bandwidth. Netflix breaks each video into 2-second segments and processes them independently via a DAG of operations. Kafka distributes jobs to workers, and simple storage service stores intermediate results. This orchestrator splits a video into segments, builds a DAG for each segment, and sends jobs to Kafka. Each segment is processed independently, allowing parallel transcoding. Netflix streams via playlists. The client fetches a manifest listing available renditions, then requests segments independently. The ABR algorithm continuously monitors throughput and buffer to select the best bitrate. This manifest builder sorts renditions by codec priority, then bitrate. It generates an HLS manifest that the client uses to request segments. Filtering by client capabilities is critical. Netflix's recommendation system is a multi-stage funnel. First, candidate generation produces 500 candidates. Then a deep neural network ranks them. Finally, re-ranking applies business constraints like diversity and freshness. This ranking pipeline builds feature vectors for each candidate, runs them through a TensorFlow model, and returns the top 20 scored titles. Features include user embedding, title embedding, current hour, and days since release. This is the same issue we highlighted at the start. Here's exactly why that happened. During the Super Bowl, a newly released movie became suddenly popular. Content Delivery Network edge caches missed, causing requests to cascade to regional hubs and then to the origin, which became overloaded. The hit ratio dropped from 95% to 40%. The fix involved deploying an emergency cache warm-up script to prefill popular content based on regional trending data. They also increased origin capacity and added a Redis cache layer in front of the origin. Backpressure on Content Delivery Network edge servers limited concurrent origin requests, preventing overload. This is the mistake that caused the Super Bowl incident. Without pre-warming, a sudden spike in popularity causes all edge servers to fetch from origin simultaneously, overwhelming it. Always pre-warm caches based on predicted popularity. Using Cassandra for both heavy writes and reads can lead to slow reads during compaction. Use Cassandra for writes and EV cache for reads, deriving read models via event-based CQRS. Without a circuit breaker, a slow downstream service can block all threads, causing cascading failures. Always wrap remote calls with Hystrix or Resilience 4J, set short timeouts, and provide fallbacks. The article mentions pre-warming caches based on ML predictions, but doesn't show how to implement it. Here's a concrete example of a pre-warming function that fetches popular chunks into the Open Connect cache before a release. The article correctly distinguishes cache miss storms from thundering herds. A key nuance: in a cache miss storm, the origin sees a flood of unique misses for the same key, not repeated writes. Mitigation includes request coalescing, deduplicating in-flight requests for the same chunk, and backpressure at the Content Delivery Network edge to limit concurrent origin fetches. To prevent multiple edge nodes from fetching the same missing chunk simultaneously, implement request coalescing. This snippet shows a simple in-memory deduplication mechanism for pending origin requests. Here's how to diagnose common issues. Check the Content Delivery Network edge cache hit ratio for the user's region. If it's below 80%, investigate cache warm-up scripts. Monitor Hystrix circuit breaker dashboards for cascading failures. Use Spinnaker to roll back to a previous stable version. Let's run through some common interview questions. How would you design the Content Delivery Network cache hierarchy for Netflix? 2-level cache. L1 Open Connect appliances, SSD, L2 regional hubs, HDD. Pre-warm based on ML predictions. Use consistent hashing. Monitor hit ratio per region. Why is Chaos Monkey effective? It forces teams to build resilient systems by randomly terminating instances. Implement with a scheduler that deletes pods during business hours, starting with low probability. Explain trade-offs between Content Delivery Network versus centralized origin. Content Delivery Network: low latency, high throughput, but cache consistency eventual. Origin: simple, but high latency and single point of failure. Netflix uses Content Delivery Network for 95% of traffic. And a few frequently asked questions. Which database does Netflix use for user profiles? Cassandra, one of the largest clusters, ~2,000 nodes. How does Netflix prevent cache miss storms? Pre-warm Content Delivery Network caches based on ML prediction of popular titles. Also auto-scale microservices and use Spinnaker for rapid deployment. What is Chaos Monkey? A tool that randomly terminates production instances to force engineering teams to build resilient systems. To summarize, Netflix system design is a masterclass in distributed systems at extreme scale. The Content Delivery Network is the most critical infrastructure. Circuit breakers and bulkheading prevent cascading failures. Use the right database for each workload, and chaos engineering is not optional. Ready to go deeper? Up next, Design Dropbox, then design Slack, then design a rate limiter. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.